started. All right. So, welcome everyone. Session 4. Probably the least well prepared. I'm sorry about that. But first, we anyway have to finish up what we didn't finish last time. We a little bit at the end didn't have time to do the demo, and I think this was the slide we ended with last time. Wanted to show you at least this slide here. If you want to look at your gradients of your diffusion sequence, you can load them into DTI prep. You can click here on the F, and this the sphere display, and this is the view that you can get. You also get a slider. Don't see that here, for the opacity of the sphere, so you can see through, particularly you have multiple shells. That can be quite good. The other two things you see up here, that's for when you run the motion correction in DTI prep. It will show you actually where these gradients move towards after the motion. And also you see which ones get removed, so that in case you have any kind of correlated rejection of data, in the sense that whole parts of the sphere get rejected, you would be able to see that here as well. We actually have a small tool that was developed by a former postdoc of mine that does a Monte Carlo analysis of the signal to noise before and after the quality control. The problem is it takes about a day to compute, which is why we didn't include it in DTI.
So actually I have one question. Is this possible to see it in the most recent
no.
versions of DTI prep?
The most recent version of DTI prep, that I wanted to just say that something is off with the bug. You can go here, it's not going to show it, unfortunately.
Okay, but do you know how far back you have to go with DTI prep?
I think pretty far right, like 1.1 something.
1.1.
All the way to 1.1.
But it's on Nitric. You can download also the old version. And this is academic software. We're not keeping everything up to date, so we'll definitely need to add that to correct that. It's in there, it's just not sure what the bug is. All right. Then one thing which we didn't talk about much is once you run, top up, FSL, once you run the OpenMP, DTI prep. So we do this also visual quality control, where we're doing investigative tractography. I mentioned that at the beginning, but I didn't go too much in detail. And one reason why we do this is there's a lot of things you don't see in just by looking at the tensor image or by looking at the individual DWI images, such as if there's a consistent bias in the image. So what I usually do in my studies is we go and track the major tracts. And I'm going to quickly show you how we do that. With 3-4 landmarks we set, and we just look at how the data is appropriate or not. And I have a small example in Slicer that I'm going to end that part with, and how to do this. So let's go over to, one more slice. I talked about this one, is a must, otherwise you get crap data. And FSL finally has detection of bad DWIs, which is great. Unfortunately, it does not remove them, but correct them, which is, I don't know. Depends on what you're doing. Best, in my opinion, is combo of FSL and DTI prep. Of course, with the new version of FSL, DTI QC has become extremely time-consuming. Before, with DTI prep, you had to wait 1 or 2 hours. Now it's become a matter of days if you run it on a single CPU. If you use the long leaf, then you can run it in a few hours if you use a fair share of CPUs to do this in parallel. All right, Slicer demo. I hope that everybody can see this Slicer. So this is Slicer. I've loaded a baby connectome dataset. You can see here, of course you can read it in the back. This is a 31-month-old subject. I actually don't know whether that's been a sleep scan or an awake scan. 3 years is a tough age to actually get good scans. That's also the reason why I chose that, is because I expect actually to see some motion and so on. So it's a bit more interesting to look at. In Slicer, you have, if you load it, this is the volume module. You can go all to the different DWI component. And you can see here, just by looking at the brightness changes, which ones is the higher or the lower shell. So this is, for example, a pretty high shell, and you can see how the image becomes quite noisy, and in part very difficult to assess what is part of the signal, what is part of the surrounding noise that you can see. This is a trying to think which one. This is a 2 shell sequence at 1,000 and 2,000, if I remember correctly. And so this is the 1,000. This is the 2,000. Just goes back and forth until it hits the baseline, which is of course much higher resolution, much higher SNR. Instead of changing the manual to automatic here, it kind of like auto adjusts. So you can see that, so you don't have to go back and forth. The auto adjustment works decently in Slicer, but it's not perfect. So sometimes it overcorrects. And so what you can do with this is you can go through the slices and see where there's bad stuff. And you can also sometimes see there's motion from one slice to the next. If you look here, you can see the brain going back and forth in part, and also you can see data, like for example, this one here, that's not a good baseline. You also have this one data set is probably not good. That is motion. You see here the kind of like jaggedness in the image. Yeah. And so you load that. What the first step is, you would run top up. Also, we first extract the baselines. So these are the baselines. And from the baselines, so these are the baselines. And from the baselines, we then correct for the APPA. If we put them all together, what you can nicely see is that the first few sets are AP, and then it switches to PA. I'm not quite sure you can see this. So this is PA and then AP. And that's, of course, pre-correction. So now you run top up, and when you run top up, that's hopefully all gone, more or less. And what you'll see, it's not perfect. So it's a third order approximation. So here's the change again. So it's not perfect. You can still see that this one is more elongated, and this one is a little bit more compressed, but it's much, much better than it used to be. And also what you can see is actually a fair share of those B0s probably should be removed, like that have artifacts down here or on these here. So one could really think about why you may want to run first some kind of a DTI prep to get rid of the bad B0s and then run top up. The downside, and I mentioned that last time, of that is that you have to adapt your scripts a little bit more to be a little bit more smarter, because your configuration has to change from image to image. Following that, we're applying top up at eddy, and that's now a corrected image. It should have no more motion on it. It has eddy current artifacts have all removed. Now there still should be bad data on there. Actually, I know how I can find out. So after this, I ran DTI prep. DTI prep gives you two outputs. One, two identifiable outputs that's not an image, such as an XML data that has stored all the details of the QC, plus a text file which is a little bit more human readable and gives you kind of like an overview of what happened during the processing. And that text file, I'm going to show you that text file. Right, so this is that text file is an output of DTI prep. And one of the things you can see here, so the first step is the slice-wise checking. It shows you which gradient found bad slices. And you can see here, if you have a gradient that has multiple bad slices, they're all listed here. So obviously, gradient number 101, DTI prep thought, well, that's probably a pretty crappy gradient. There's a few more, like 111, 106, 102, and then now that is one way to go. So now we can go here, 100, and what did it say, 10? 101, thank you. Yeah, looks pretty bad. So, and overall, pretty bad, not just a single slide. And I think 106, it found one bad slice. I don't know where I can see that right now. It actually lists the slice, and you can go and find that. And again, I think 111 was bad. Yes, you see that here too. And so you have to keep in mind, particularly if I go back to 101, if you enable in FSL the interpolation, it will try to detect the bad slices and then interpolate those data. Even though I would say even on the slices that are not detected as bad, there's so much things happening that probably you shouldn't use those slices. So I would not use anything from that DWI. That's better. On the other hand, there may be other ones where DTI prep says, "Oh, look, there's only one slice that's rather bad. This one here, I cannot even see it." Let's say if I would take that slide, yeah, interpolating is probably fine. So that's what I mentioned last time, that there's some DWIs you probably want to throw out, and other ones where interpolating data is probably fine. So now if you run DTI prep, that's the, get this one out, go to that one. And now that slice is of course not in there anymore. So if I were to go to 101, you won't find it. And then the last thing I wanted to show is this is now the DTI that we're getting out of this. And on the DTI, you can see it's very nice high contrast. This is a very, very nice signal to noise. It's also nice resolution. This is the baby connector. This is higher resolution than most of your studies will have. This is at 1.5 millimeter isotropic. And so what I would do now as a final step of the things, I would do this investigative tractography. I can quickly show you how that's done. This is the marker in 3D Slicer where you would place landmarks. Now you place landmarks where you would expect the major tracks to go through. There are probably other tracks to go through there as well, so you're not just getting those tracks, but a little bit more. But the main thing is just that you can see at least those major tracks. What I usually do, I go to the Chinu, SET1, splenium. This is actually a very nice case in that the subject was very nicely straight in the scanner. Most of your subjects are not going to look like that. They're going to have the head more like this and so on. So you may have to scroll several times until you find that middle slice, mid-sagittal connector. And also going for the cingulum, which is very nice and visible here too. You can also go for the fornix, which you can see here as well, just below the corpus callosum. I usually also like to see something in the temporal lobe, not just in the center of the image. The center of the image is usually better behaved. So I go for the uncinate. The unsynod is the tract that goes from the temporal lobe to the prefrontal lobe, and that's the location where it crosses over from the temporal into the prefrontal. You can see that this blue area that is at the medial section of the temporal lobe. And I usually also go and do something for the internal, the cerebral spinal tract. So once I said those things, I go and here on the diffusion tractography seeding. That name actually changes from version of slicer to slicer. It's called tractography seeding in the newest version. In the older version, it's, I think, fiducial fiber tractography, but that's just a name. It's all the same tool. And the defaults are usually set more for an adult brain, so I change those away. I always want to be permissive. I want to see kind of like what's there. I select my fiducials and I say click update. Now I see here you have your fiber tracts. Another thing is right now, this region size that basically makes a sphere around your fiducial. And within that sphere, it samples seeds for fiber tractography. And in order to get more tracts, you can increase the number of maximum number of seeds. I go that to higher, and this going to 6. So that now I have a 6 millimeter sphere. And always I click here and update. Now I can check here, and every time I change here something, it automatically updates. All the versions of Slicer don't actually have that. They always update. But here it's actually nice that you have to click, so that in case you by mistake change something, it doesn't take long for you to wait to see this. Let me just visualize that 3D, and you can see that here the fibers are visualized here by the average orientation along the fiber. So blue fibers would be up-down. Green fibers are going to be mainly front-back fibers. Red fibers are going to be mainly left-right fibers. Now, I'm not quite sure. Well, this is more yellow, I guess. So the chinu, very nicely visualized. The splenium is largely there. And we also have some tapetum parts. The cingulum is actually very beautiful. It's very rare that you see nice quality like that for the cingulum. And here, this is the unsynod, this one here, that goes from here to here. Looks fine too. So everything is fine, everything is there. So this would be a nice and passing tractography. I don't have an example here to load of a bad tractography, but what you would see is kind of like that all tract seams, instead of going, let's say, I would look this from above, rather than them going forward, that they would be kind of like drifting. Kind of like all would be drifting to one side to another side if there's an issue with with that gradient, or it could be an issue where everything is kind of like drifting to the back. You would then see this one here kind of like as if upwinding. And depending on how big the issue is, rather than the drift, you would see that all of them are just early terminating. That's another possibility. But basically, all the tracks you get are pretty short. And that's very much indicative of a problem with the scan, and with the scanner actually, not necessarily just with the scanner. Any question on this slicer demo? There's a very nice tutorial in generally on how to use slicer and diffusion data online that you can get from the Slicer website. So I'm not going to do too much of a Slicer specific demo.
So there's actually a tutorial also listed on the natural website that actually shows you exactly where to put your, because I actually didn't know my anatomy all that well. So where to put your fiduciary, especially for some of these more obscure tracks like the unsynod. Well, for me, more obscure. And there's yeah.
I think most people don't know white matter anatomy. That's
yeah.
not.
So
People know what kind of like the hippocampus is and the amygdala maybe.
Yeah. Well,
But if you say ANSINET, they're usually lost.
Well, and specifically where to look on the diffusion imaging. And actually, there's another website that does that too. Actually, I should put the link on there. And then there's actually this cute little app for anatomy, just as a brain tutor 3D. That's actually like my quick fixed reference on fiber tracks. So I think it's like, I don't know, just for
Nice, yeah. So, and in general, of course, particularly about any kind of anatomy, you can find a lot of online information. And for the tracts, actually, Wikipedia is a pretty decent description of most of the tracts. They don't tell you how to track them in Slicer, but it tells you where does it run through, where is it going, and most of the tracts from neuroanatomy are listed in Wikipedia.
Is there any way of automating the placing of the markers and getting those images out in case you have, say, 10,000 scans you want to do quick QC on?
Well, you probably could. I mean, one can just take a simple template space, like a template you have, place those landmarks there, which is the template, and like affine it, just simple affine registration, and propagate the landmarks that way, and then do an automatic tractography. The problem still is somebody has to look at it. A automatic quantitative assessment of that tractography is probably possible, but non-trivial. Like one would have to first develop that. We do have also an additional tool, a regional QC tool that does something similar to that. It basically registers a prior atlas with regions and then looks in those regions whether the distribution of directions is as we expect. We have not found that to be very sensitive, unfortunately, which is why we're not simulating. But yeah, one particularly if you have lots and lots of data, you would wish that this is not necessary. But I have not found yet a good substitute, because particularly this one here, is something that you want to do when the data comes in. This one here specifically identifies a problem, ongoing problem with the scanner or scanner electronics often. It rarely is something that has to do with this, like with motion or anything like that. Motion you would see before getting here. This one here is like, oh, there was no motion, everything is good, but somehow something is bad. And that somehow relates to either the scanner or interaction between the scanner and the individual, such as the Siemens TIM Trio data used to have a vibrational artifact. If you get TIM Trio data from like 2010 to 2012, there was a lot of incorrect bad data that is not correctable because there was an interaction between the individual and its weight and the scanner with that created a vibration. The vibration was at the frequency of the acquisition of the data, so there was an interaction between them. Yeah.
I was just wondering, what's currently the standard? Do you do like a full brain tractography and then label each file?
Just the way I did it right now. You just do 5 or 6 fiducials that you go, because this is only for QC purposes. It's a throwaway tractography.
Okay, no, I mean that for analyzing these. If you want to analyze a certain fiber bundle, you generate like these separately and then analyze them, or just generate the full tractography and then label, and then analyze.
That actually segues into my next section, which will be the atlas building and fiber analysis part. But it's a good question, and there's different methods out there in the field. Particularly, we have to first look at 2 things. Let me actually start up that next, because then I'll talk about all that. Any other additional final questions on this stuff? Otherwise,
I'll just add that we recently had the experience with this when it was a data conversion problem.
Yes, that can also be.
So the tracks look really wonky. They just look kind of truncated and twisted because there was a conversion between.
You may remember from last week, from last session, where I talked about measurement frame and gradient directions and so on that are in the DICOM file. And that was exactly such a thing, where what was in the DICOM file was, I think was correctly taken out of the DICOM file, but not the measurement frame. And when we then got that incorrectly DICOM converted data, it looked all crap. Now, when we did our conversion, it looked all good. So now we're doing the DICOM conversion for the project, not the outside side. They was using Mink tools. I'm pretty, so that was MNI, and I'm pretty sure they'll update those tools with our feedback. But for the time being, we want to make sure that incoming data is getting QC, so that when there's issues, we can, within the reasonable period, we can let them know there is issues with the scanner. All right. I can close this here. All right. All right. So this is the next session. This is about now more one particular analysis framework, although it can be used in different ways. But it focuses on the analysis framework that was developed here at UNC, initially by Guido Gehrig and his group. They started it back in 2002, 2003, before I came back. And then in 2004, NAMIC, which is a National Alliance for Medical Image Computing, was a NIH-funded National Center for Biomedical Computing. And it's actually a network from different universities, and UNC was one of them. And our main contribution to NAMIC was this diffusion analysis framework that Guido, and also to a certain degree, I helped developing. Guido was more the one driving the methods, and we were then the one creating the tools around the methods to make this actually work. The things we will talk about are these different steps that are used in this analysis framework. The main thing is this is a fiber-based analysis framework. So we're extracting fibers and then analyzing the information with respect to those fibers, such that we have a fiber-specific analysis and not what is in TBSS, this localized analysis, but it's not specific to a fiber, more to a certain region close to the white matter skeleton. There are other alternative fiber methods, fiber analysis methods out there. There's one actually in FreeSurfer. It's called Tracula. They just are releasing one specifically for infants. They call Traculina. And I'm actually due my reviews. Oh, maybe I shouldn't say that. Anyway, I'm a reviewer for it, and I should send my reviews back in. The main difference is this one here uses an atlas space where you do the tractography, and the tractography gets tracks that serve as a region of interest for all your subject data. Whereas Traculina and also some of the other tract-based analysis frameworks, they track on the individual data set. And they have a method such that what you track on the individual data set is kind of comparable. Now that's very difficult, that kind of comparable tractography on each individual data set. There's another more atlas-based fiber analysis methodology that comes out of the Loney, which is at the University of Southern California. And it's a pretty decent one. The thing that they're missing is an analysis along the tract. But they do something actually quite similar to what we're doing in our, that you build an atlas and you do tractography, in that case, automatic tractography in the atlas as a way to get to regions. All right. So, and most of these tools that we developed as part of this NAMIC toolset are extensions and slicers. So unfortunately, every time there's a new slicer version, even subversion, we have to go in and change our extensions so that you'll see if you download a specific version, some of these extensions are there and other ones are not there because we need to go and update them. So we found it actually to be rather cumbersome to keep these updated. So what we're doing now is actually we have our own slicer version. It's called Slicer Neural. And that's still in development. That's actually Juan has been pushing that, and that's really great. So that we have our slicer version that comes with our extensions. So you download our slicer, it has all these extensions there that you need. And once in a while, we may update that. But we are not bound to the slicer updates anymore. And so this is kind of like, again, the overview. So what the idea is, you build first an atlas, which counts as a reference space for your analysis. You do atlas building, then you do tractography in that atlas, and then you do extract profiles of tensor properties, or if you have higher order stuff, of higher order properties along the tract. And then you get these profiles, which are now functional data along the tract, and you do a functional analysis of that data. If you want to make it simple, rather than getting a profile, you can also just take this profile and compute an average value. Then you have an average FA, let's say, for the uncinate per subject, and do more traditional statistics. And just here to show what are the individual tools that you use for these individual steps. So quality control, we talked very close, DTI prep, top-up eddy, DTI AtlasBuilder to build the atlas. There is also in ANTS, when you get ANTS, there's an ANTS AtlasBuilder there. Unfortunately, it doesn't directly segue into DTI data. So you need a little bit more sophistication if you want to use that AtlasBuilder to do it, to apply it to DTI. Then we track the tractography. We do the tractography using AutoTrack. That's a new tool that we developed in the last year, as well as then clean up the tracks using Slicer or Fiber Viewer Lite. And the extraction of the profiles is that DTI Atlas Fiber Analyzer, and the analysis is with a tool we call FATSTR. FATSTR is currently really nice for cross-sectional data. It does not support at the moment longitudinal data. This one here is actually based on a MATLAB tool called FATS. In the MATLAB tool FATS, there is a longitudinal version. It's just not supported by our graphical user interface. So if you are MATLAB savvy, you can definitely use the longitudinal version. So as you can see, the first step after the quality control is to build an atlas. So we're going to be talking about DTI AtlasBuilder. That's going to be the main thing probably for the remainder of the session today. This DTI AtlasBuilder, it creates a general average space where you can use that as a reference. And we do that, for example, in our 1- and 2-year-old DTI Atlas we disseminate. We have in there something like 60 tracts. People download it more for also educational means to see where the tracts and so on. But, or for when they want to do an analysis in the given standard space, they can use that UNC 1- and 2-year-old Atlas space. When we do, in generally, our analyses, we use this Atlas space that we computed, that 1- and 2-year-old space, as a prior to build the new Atlas in, so that we we have all atlases built in a similar reference space. And when we build such an atlas, we actually have several steps that we do this. So DTI AtlasBuilder does this on the inside. And it's largely 4 steps, although as you can see here, it's really 3. As this one here is really 1 step and involves actually a conversion step that is not really functional. It's just a conversion of data. The first step creates an affine atlas. From the affine atlas, we then compute a deformable atlas using a unbiased diffeomorphic tool. It's called Greedy Atlas. And that's that's software by Saron Yoshi that was developed quite a while ago. And then from that Greedy Diffeo Atlas, we create a symmetric Diffeo Atlas. The reason why we put this in here is this allows us to really call our atlases unbiased with respect to the data. So you can shuffle the data however you want, present it however you want. you're going to get the same atlas out of it. If you were just to run this part here, usually you have a problem that you need a first decent image to register to, and that decent image is a prior. Here, our prior in this step is the unbiased atlas, which makes the whole thing unbiased. People have argued that this is not really necessary. Just doing this enough times, this final step, gives you something very similar. And mathematically, that's not exactly correct. But from a viewpoint of pragmatic, actually applying it, practically it's probably the same. There's probably not much difference. And that actually is what Ant's atlas building does. It basically does this step. Just in what we usually do, we run this step, which is this final diffeomorphic atlas. We run that twice. If you do that with Ant's atlas building, this is done until it converges, which means many, many times. So I'm going to now go through each of these steps a little bit more in detail. So in order to have a setting where we can apply a diffeomorphic registration, you always need to solve the affine registration. Now, that's easiest done if your atlas is already kind of affinely aligned. So that's why we build first an affine atlas. What we do basically here is a two-step process where we register all our data affinely to a first template, kind of like a reference-based template that can either be provided optionally, or if not provided, so it will simply be the first data set in your list of inputs. Now, that is a little bit unbiased. So that's the only thing by which we are biased, because we have this initial affine template. That I don't consider to be that big of an issue, because it's really just sets where in space is our atlas. It's going to be here, here, or here, and how is it oriented. So the first loop basically registers everything affinely to that first initial template, and after the first loop, we compute an average of all of these affinely aligned data. That gives us the first DTI atlas, and then we register again everything affinely to that one. That gives us the final affine DTI atlas. What you can see here is that there's two steps in all of these. There's one, the computation of the registration information or the transform. That's done using FA data. So you have your DTI, you compute the FA, you actually intensely normalize it. You change the histogram to a such that all the images have similar distributions with respect to that, so that if you have, let's say, data where due to a disease or disorder, you would have lower FA, you wouldn't want that to influence your registration here. So that's why you do some histogram normalization to the data such that they appear all about similarly for the purpose of the registration. And once you compute that transform, you apply the transform not to the FA image, but you apply it actually to the DTI image. So you go back to the DTI image. What you get out of here is really a DTI image, and then you average, not the FA, but you average those DTI images. One thing that you have to be aware that it's pretty straightforward how to average or how to deform or transform a single scalar image such as an FA. But actually for a tensor image, that is mathematically ill-defined. So there's all kinds of assumptions that you have to do, and there's different settings for that, and the tool allows you to change that. What we're doing is usually a preservation of the tensor volume, as well as preservation or rotating or preservation of the principal directions. Yes?
If you have like a T2 image or like a T1, is it better to use it for the registration steps instead of the FA?
Well, if you would have a T2 image that's perfectly registered into your diffusion data, then yes, but that rarely exists. Usually, if we do a registration of a prior or an additionally acquired structural data set, that registration is imperfect. And I don't think you want to use that as creating your atlas, where it's about aligning fine white matter structures, because the FA image is actually very nicely sensitive to such fine white matter structures. So there are alternative methods out there that, rather than using the FA in between to compute the transform, directly compute this on the tensor. So they have a way to establish where the two tensor images map well. That tool is called DTI, and while we've been using it before too, it's not something that's supported by the tool right now. So that gives us an affine atlas. That's kind of like a first step. Really, we don't need that affine atlas down the road. It's just an intermediate atlas that's computed only with affine alignment. The next step is this diffeomorphic unbiased registration using greedy atlas. And what it does is it computes first an unsharp mean, basically your affine mean, and then it computes a diffeomorphic registration to that mean. And when it computes that, it doesn't actually fully deform the data to that mean, but it does that stepwise. It does a little step in that direction, recomputes where it would end up, recomputes the mean, and does then recompute the registration. It does that in a loop, basically iteratively sharpening the mean as well as computing an update on the deformation. What this gives you is an average image that has minimal deformation as a sum of all the deformations for any of your input data. So this makes it also very specific to your subject data. So if you have a study where you may have atypical brain morphometry, this really is going to be something that you want to do such that the atlas you create really represents the data that you want to analyze. Now, there's one downside to this, using this, that it's quite sensitive to intensity outliers. Since this is based on the FA image again, if you have very noisy FA data, for example, if your skull stripping wasn't very good and you now include the skull has not a lot of signal, your FA is going to be actually very noisy there. It's kind of like, looks like pepper spray kind of stuff. Not pepper spray, but peppers. If you don't do this good brain masking, this can really distort the atlas building. So you want to make sure to do not have the skull in the image. And yes, well, you see this is called 2 and 3, and it just is called 2 and 3 because that's how the data is organized in DTI AtlasBuilder, because it uses its own file format. So we have to first convert it to that file format, then you have to convert it back. And that back conversion has its own folder. So that's really just one step, and has a file format step included. So now we have this unbiased diffeomorphic atlas, and that's again the DTI. It creates a DTI, an average DTI. So we are now running 2 steps of an ANTS atlas building, basically, where we're using ANTS to register all of our DTI data to the current DTI atlas. And like in the affine case, that is, we get the DTI, we computed the FA, we normalize the FA, and then we register that to the current DTI atlas. And that gives us a deformation field. But when we use that deformation, we apply it to the tensor image. So we propagate the tensor image, then average the tensor image, which gives us a new DTI atlas, which after that step, that is called the final DTI atlas. And because that is now different from the prior, we recompute the mapping into that atlas. That's the second loop. Basically, we run, in this case, ANTS twice. What it actually does under the hood, it calls a module called DTI reg, which then calls ANTS and does all the stuff. DTI reg can also be used if you just have a data set and a prior atlas, you want to register the two together, you can just use DTI reg to do that. One thing, and you'll see that if I get, when I show you all the details of the tutorial, is by default it uses an older tool. So make sure to change the default away to ANTS. And we had some unfortunate thing where we forgot to do that, and then we had to rebuild the atlas, and we had done already part of the analysis. So make sure you change that default. And probably the next version of the DTI AtlasBuilder will simply change that default. This shouldn't happen. The data organization, the way it works is it creates an output folder called DTI Atlas. And in there it has 4 folders, 1 for the output of the affine, 2 and 3 for the output of the unbiased, and 4 for the final resampling. When you're happy with your DTI Atlas, you can actually remove 1, 2, 3, just throw it, and then the first resampling as well. The only thing you really need to keep is in the final resampling of the second resampling. That's all you need to keep. The actual final atlas is stored in the final resampling folder. And if you want to look at the scripts that it runs, those are in the script folder. As well as it creates 3 additional outputs. One is the parameters that were used, that were set for running it. If you ever want to know how did I run my DTI AtlasBuilder, it's automatically saves that, as well as the input data set, as well as the output results. So what this CSV has is now a CSV that lists for each input data set, what are the output files that were created? Where are the affinely aligned data? Where is the unbiased register data? And where is the final resampling data? That's all stored as paths in this result CSV. The reason why it writes out, this CSV is an input to some of the other tools. So you don't have to do that by yourself when you generate inputs. Once you start rolling here, once you have the input into the DTI AtlasBuilder, you can take this to all the other analysis tools. I'm going to quickly run through the GUI, how you set things. The GUI itself does not have any visualizations, so it's thought that you use Slicer as well as MRI Watcher. I'm going to talk more about that for any kind of the QC, etc. While this has a GUI, you can run DTI AtlasBuilder fully on the command line as well by just giving it the parameter files that it uses. But if you, for example, run this for the first time, you would run the GUI, you can set your parameters, and then you can also run it from here, or you could just save the parameters and then run it on the command line, however you prefer. This is this tab is the main tab that you can interact with. Theoretically, you do not need to touch any of the other tabs if you want to use the default. But if you remember just from 2 slides before, I said you have to go and change the default for the ads. So at least you have to change one thing. What you can do here, you can either load a CSV file that lists all your subject data, or you can just click on plus and minus to add and subtract data. When you click plus, a file dialog comes up, and you can select individual files, or you can, with the control, you can select multiple files, and it will keep adding them here. If you now have some in here, and you want to remove them, just select them here, and then you click remove. The Save Data button is not necessarily, you don't have to use it because it will save it as soon as you click Compute. But of course, if you want to run it on the command line, then you have to make sure that you save it. Yes, and then there is the output folder. So you said where it should store DTI Atlas, and in that folder, it will create a folder called DTI Atlas with that organization I just mentioned. And then this is where you give the additional template. Now, one thing that's maybe non-intuitive and specific is that all of the things that you mentioned here are the DTI images, because it's really DTI AtlasBuilder. But for the affine registration, here you give it an FA image. So it says you see, give a template for the registration, use of an FA template. So FA. But it doesn't need to be a somehow histogram normalized FA. It does that, but it has to be an FA image.
Can I ask one
Yeah,
question?
sure.
It is important that the FA image be at the same resolution as your data?
It is not necessary that it's at the same resolution. It depends which registration method you use. If you use daemons, so the old one, yes, it would be necessary. It is actually not necessary for ANDs. Whatever you use here as a template, it will automatically actually also resample. So the main thing is, though, during the computation, so you get a different computation if you do the resampling before or after. So we suggest if you have a different resolution than your FA template, I would first resample the input DTI data to that same resolution before you do the DTI AtlasBuilder. But you can also, it's perfectly fine. It will give you an atlas. If, let's say, the FA template is at 111 and your DTI data is at 222, your DTI atlas will be then at 111 finally. But during the computation, it will compute it based on your 222. It will deform the 222 to the 111. ANDs can do that. That's nice. So if you're all happy, you just click compute and let's go. Down here, you have an additional button that you can say, well, I want to override everything that's going on. Then you can click on override. Otherwise, if you don't click this, it will not override what's already there. This atlas building can take longer, let's say 1 to 2 days. Let's say your machine crashes. The good thing is, it will just continue on from where it was. And so if you don't click this, it will continue on from where it was. If you click this, it will override what it has. It will start from scratch. Just as if you would have actually deleted the output folder. It's the same thing here. Then, if you realize that the affine registration has gone wrong, that's actually probably if there's a problem with DTI AtlasBuilder for an individual data set. The most often you can see is that because your data is kind of like, some subjects like this, some subjects are like this, the affine registration is just not able to recover all that initial affine alignment. You'll see that, if I go back, you have here an affine QC button, where if it's done, and you don't even have to wait for all to be done, when the first step is done, unfortunately, we must show you, but you can then click Affine QC and it will call MRI Watcher. MRI Watcher allows you to load lots of data sets, different data sets, and look at them jointly. And so you would be able to see, oh yeah, everybody's aligned except for this case. That guy is not aligned. So, and it would, since it also mentions which the file name and the file name, the name of the data is encoded, so you would know, okay, subject, I don't know, X, it has been badly aligned in the initial affine atlas. What you then would need to do, you would need to go into that atlas folder, into the affine atlas folder, and you can give it an initial affine transform. So you can either give it a transform or initial aligned image. But you have, so if you give an initial aligned image, you have to give it both, the transform and the image. But you can also just give it an initialization of it, and that's how it's described here. It's basically, you can use slicer to get to a transform, do that manually, save it into that folder according to that naming that naming convention, and then when you're recomputing it, it will use that. Now in this case, you would either have to click the recompute button, or you just remove the output of that step, while keeping, of course, your initialization file. And then rerun it, and it will use it. Now, with respect to options, you can, for the affine atlas, since it's kind of like the first step, you can add a safety margin. So if your data, particularly with DTI data, you see that a lot, if your data is quite tight, so the sequences are such that the slices may cut nearly all or even part of the cerebellum, or very tight or very tight up on the top of the brain, what you want for purpose of the DTI AtlasBuilder, where you have larger heads and smaller heads and everything is done well, you want to add basically a safety margins around the images. basically adds empty slices. And that's just for the purpose of the diffeomorphic registration to be working well. If you don't do that, but you now have a slice where the first or the last slice or neither of the slicing directions has still information, you can be sure that your DTI atlas will look badly, because it's just the way diffeomorphism is computed mathematically. If you have an image where the first slice does not have signal and one where one has signal, that's just not, from a diffeomorphic point of view, actually mappable. Then the second step is for this unbiased diffeomorphic atlas registration. Unless you really know what you're doing and you're reading up on the methodology, don't touch this. It's better not. This part here is general, not just for the atlas works. That you could change it. And generally, I do not suggest you do. This allows you to specify how do we interpolate tensor data. So you see here tensor interpolation using log Euclidean. That's kind of like understood to be fast and acceptable. You can change it to other less acceptable ones if you want to do so. The tensor transform, the PPD is principal preservation of principal direction, so that when you transform the tensor, the principal direction goes with the rotation of the local frame, whether that's affine or a deformal registration. This results in more accurate transforms. But from a viewpoint of mathematics, there's actually not a good reason why this is the right way versus another way. There's several methods out there. We use PPD as it gives us the most reasonable results from a viewpoint of tractography. Then final resampling. This is the default, the way it shows up. That's what I'm saying is do not use brains here. That uses brains log daemons. I say change it to ants. And as soon as you change it to ants, actually this stuff here changes. And these are the general ants settings. So if you're used to ants, this is pretty straightforward. The only thing that you probably have to adjust to what you usually do is the DTI data is lower resolution than your structural data usually. So that changes things a little bit. But the default settings here are actually pretty decent. So if you have human data, whether these are infants or adolescents, just use what the default settings are in general. They're pretty decent, except for if you have monkeys or something like that. Then you may want to adjust your sigma for the Gaussian. 3 mm is a bit large for monkey or rodent data.
I'm noticing that the region radius is 2 as opposed to 3.
Yeah, you can do 2 or 3. I think both are acceptable.
3 is 3.
I think we did 3 because we also had older atlases built at that same setting and want to be consistent. But you can use either one. This region radius, by the way, is in pixels, not in millimeters. Only the sigma is in millimeters. Because it also doesn't make sense to specify the region radius in millimeters because it's a kernel. So it really makes sense to specify it in number of voxels. So yeah, there's a load save menu where you can save and load all the data. If you run compute, you don't really need to do that because it's going to save it with the build atlas anyway. The CSV files that it uses for data, that's how they look like. It's basically the input has to be some version of this where it assumes the first column is your ID, and the second column is the DTI image, the path to the DTI image. So here it's very simple. Just use ID 1, 2, 3, 4, 9. But if you actually have a subject ID associated with your study, you can put in here the subject ID. You can even leave out that first line. And what it will do then, it assumes everything in the name of the file up to the suffix, up to the extension. is the ID, and it will, and that matters for the output. So when the output naming will be related to the ID or to the input file if no ID is given. Yeah, so you can, if you have a previously created CSV, you can just use load data to do that. And usually we do that, particularly if we run studies with, let's say, 100 subjects. You don't want to go and click 100 times plus, particularly if they may be distributed. So you can write a small script or just even on the command line, something quick that just takes all the file paths and redirects them into a file, and then you can load that as a CSV. If you want, you can add a first column with the IDs, but as I mentioned before, that's not necessary. So yes, quality control, this is affine, this is after the second step, so the greedy, diffeomorphic, and this is the ANS diffeomorphic. Usually, this and this step you want to look at. When I look at it, I just look at the final QC first. Because if the affine registration failed, it's going to look crap here. And then if an individual data set looks bad in the final QC, I go back to see, was it the affine QC or not? And usually the affine QC is the culprit. The other thing that you sometimes see is if, let's say if your process failed while writing a data set, let's say, there was not enough space on the disk and so on. So then you will have maybe a partial image on disk, and then that case may be bad too. That's the other possibility. This is how MRI Watcher looks. So it loads them all and displays them like this. Now, if you build, let's say, DTI Atlas of 100 subjects, it will load 100 images. So one way to do that, because it's going to take forever to do that, is it will actually, on the terminal, it will output what it calls. You can take that output of the MRI Watcher line and maybe divide it into more manageable steps. That probably is a feature we should add, that it should maximally load, I don't know, 30 or 40 at a time. And what you see here, so yeah, this is the affine registration. This is the affine registration. And at the end, what you should be able to see is that your average that is computed, this is the last image to show, should look exactly like all the others. Because it shows you how the images have been mapped into the atlas. If our atlas building worked, you should actually not be able to detect any individual differences. You will, it's not perfect. Particularly when you go to the outside of the brain, of the folding of the different cell sign gyri. It will not be perfectly able to restore those. All right. And I'm actually going to skip this. This is just, these are the tools it uses. It will set those by default, but if you want to set it to your own tool, let's say you have your own ANS or a different version of one, you can do that easily here. And it stores that, when it saves all the parameter files, it stores that with it. And yeah, you can, if it's empty, you can just click on default and you will go in and grab it. Like it mentions here, it has a environment variable that you can set where it will go and look for that. If it does not have this variable set, it just goes and looks at your path. Yes, and this is just reset. Okay, I'm gonna skip this. And you can load save that things separately. So that if you have a certain system set up and you may want to build multiple atlases, you can save this once and then use it for all your atlases that you build. And it has even support for grid processing. Now, the default is made for Kill Devil, because that's when we developed this tool. As you know, those of you who are now in Longleaf, Kill Devil, Longleaf are quite different. So you would have to write in here your submit command. In some sense like this, like for Longleaf, this would be srun. So you can run your srun command with all the settings, and it will then run each individual step separately. So it will parallelized as much as it can. So each of the affine computations will be parallelized. Each of the ends computations will be parallelized. The one thing that's not parallelizable is the second step, which is the unbiased diffeomorphic registration. Because for that, it needs to actually load all data sets, because the deformation is done jointly for all the data sets at the same time. So because of that, by the way, because of that second step where it needs to load all data sets in memory, the memory requirement for that step is pretty high. You need to make sure that you run this not on, let's say, 8 GB node or something like that. You need to request sufficient memory if you run this on the grid. If you run this on our servers and you have a decent amount of data sets you want to build this over, use PAN, as PAN has 128 GB. So if you have over 100 to 200 data sets, expect you need close to 100 GB for running this. And since usually you can only do one command here, what we're doing is actually we usually run it twice. First, we run everything up to that unbiased deformation and say, run, I don't know, everything in parallel. And then at the unbiased registration, we stop it and run it just once on a high memory node. And then we do the last step again like this. And this is, I think the newest version of DTI AtlasBuilder may even have two things here. I don't remember. I should have looked that up. Yeah, so it may actually be possible that rather than running it twice, that the new version of DTI AtlasBuilder may support that directly. Any questions about this? One last thing, if you want to do TBSS with FSL, I suggest you do not use the Atlas creation in TBSS. I suggest you use this, because that creates deformation fields that are readable by FSL. And also it creates an atlas that is of much better quality than the FSL atlas. There's actually a very nice paper out, not specific to our DTI AtlasBuilder, but that shows that FSL's atlas building is a bit wonky. So you could also use the one in that comes straight forward with ANS if you want to do that. It's definitely much better.
A question: when building an atlas to look at like a clinical sample and then look at the development sample, do you put all the images together and you build one atlas, or do you do it on each clinical group? Or
so two possibilities. You could, if you want the atlas to represent both groups equally, you would have to either have a nicely balanced sample. Then you can do that. Just build one atlas. If most likely you're going to have an unbalanced sample, and since there's no way to weight the data here, what I would suggest you would build in an atlas for each group, and then build an atlas of the two groups. And what you would do is, rather than resample the image twice, you would then actually combine the deformation fields. We have a tool that lets you combine the deformation fields. So then now, while you're creating this two-step atlas building, you can still end up with one deformation field that gets you from the individual space to the atlas space. And we're doing, by the way, the same thing when we do a longitudinal atlas. Let's say we have an individual, and for each subject we have 5 or 6 data sets. What we usually do, we build first an atlas for each individual. Now we have, let's say, if we have 100 individuals, we have 100 atlases, and then build an atlas over those subject-specific atlases. And then we do the same thing, we combine information fields. I have a student actually that encodes that two-step process right now into the next version of DTI AtlasBuilder. She's not very far along. She's an undergrad, so it may take a bit. But that is definitely useful exactly for both if you have unbalanced data and expect big differences, or you have longitudinal data.
Are you suggesting 2 different population atlases to start with, only if you expect them to be very biologically different?
Yes.
Thus far in our studies, we haven't done that. We don't fall into the same group.
That
That's
is,
an atlas.
yes, also, but remember there is a an FA, that the FA images are normalized, intensely normalized. So unless you expect really dramatic differences, you should be fine. You shouldn't have to worry too much about that stuff. But let's say I have an MS population where we do expect large differences that are not going to be overcome just by simple normalization. There, I probably would suggest we would build 2 atlases first. In our autism studies, I mean, all the data we can see, all the papers in autism, you know, yeah, as a group, we can find differences, but as a group, not individually.
And even populations like our Angelman syndrome that has no white matter differences. They're
So,
not that
so that's the other
halfway
possibility.
along that scale.
Well, so Angelman's disorder, similar to, I think in the first session I showed the example of the Krabbe kids, similar to that. They're very different. There's a big difference there. Rather than building an atlas with Angelman or with Krabbe kids, we actually usually build a typical atlas and map those other kids into that typical atlas, and just assume it's going to be as good as it can be, because we don't have enough subjects anyway. And there may be not just enough subjects, there may be large inter-subject differences in that population, such as in Krabbe, but also in Angelman. We've seen actually a really big spread. So making an atlas of those just for kind of like having everything mapped into single space, I'm not quite sure that's the best way to go. We're kind of like making everybody map worse just to map those few data sets of the Angelman. But most of you do studies where that shouldn't matter. Yes. Good. All right. Thank you all.